Okay, so here's a thermal deformation example problem. So what we have is we have two different bar sections. We have a solid aluminum alloy. Here's bar 1. We're given the modulus of elasticity and the coefficient of thermal expansion. For rod 1, it's attached to a solid brass rod 2. Again, we have the modulus of elasticity and the coefficient of thermal expansion for bar 2. The compound rod is subjected to a tensile load, P, which is 6 kilonewtons. And the diameter is the same for both rods at 10 millimeters. And then it gives the lengths of the rod. L1 is 525 millimeters, and L2 is 675 millimeters. And we're supposed to find the change in temperature that will produce 0 horizontal deflection at end C. So if we think about this problem, we're pulling on the bar, so we're applying a force leading to a stress, so we'll have deformation going out. So the temperature will have to decrease to make it stay with a total of 0 deformation. All right, so givens from the problem, we know that the elastic modulus of 1 is going to be 69,000 megapascals, and that the coefficient of thermal expansion is 23.6 times 10 to the negative 6th per degree Celsius. That's for 1. For 2, we have an elastic modulus of 115,000 megapascals and an alpha value of 18.7 times 10 to the negative 6th per degree Celsius. Okay, and then we have that P equals 6 kilonewtons, and the diameter is 10 millimeters, and those two are consistent for 1 and 2. And then we have the two different lengths. So we have length 1 and length 2. Okay, so ultimately what we have going on is that this 6 kilonewton load or force is going to be applied through both bars. They're going to have the same stress because P stays the same because they have the stress, and then the stress stays the same because they have the same diameter. So we're supposed to find the change in temperature, so our governing equation, so let's write what we're supposed to find. Find the change in temperature, so delta equals 0. So if we think about this, we have our governing deformation equation with thermal expansion is the deformation, little delta, equals the force times the length all over the area times the elastic modulus plus coefficient of thermal expansion times the change in temperature times the length. So, and then we have two sections. For the two sections, we have the same A and the same force, and the change in temperature will be the same for the two sections, but our lengths change, our elastic modulus changes, and our coefficient of thermal expansion changes. What we don't know in this problem is the deformation of bar 1 or the deformation of bar 2, but what we do know, so this is an indeterminate problem, we know, So we need the deformation of 1 plus the deformation of 2 to equal 0. So once we know that, then we can have this will equal F1 L1 over A1 E1 plus alpha 1 delta T L1 plus F2 L2 over A2 E2 plus alpha 2 delta T L2 all equals 0. And so the areas are the same, so we're going to get rid of their subscripts, and the forces are the same. So try to get rid of their subscripts. Okay, so if we know all of those things, now we know force, we know length, we know area, we know the elastic modulus, we know alpha, we know L, we know force, we know length, we know area. Well, we can calculate area. Elastic modulus, alpha, and length too. So all we don't know is delta T. So now we just need to calculate the area and then solve. So that's pretty cool. So the area for 1 and 2 equals pi over 4 times the diameter, which is 10 millimeters squared. And that equals 78.54 millimeters squared. So that's for 1 and 2. Then F equals P. We're going to use it as newtons, so that equals 6,000 newtons. That's for 1 and 2. So then, if we just plugged all these numbers in, there's a couple ways you can do this. You can leave it as variables and substitute out delta T, or you can plug in all the numbers. And I went with just plugging in all the numbers. So we'll have 0 equals, we'll start here. So the force is 6,000 newtons times the length of 1 is 525 millimeters. All over the area is at 78.54 millimeters squared times E1 is 69,000 newtons per millimeter squared. And we have to add the thermal expansion component. So that's alpha 1, 23.6 times 10 to the negative 6 per degree Celsius times our variable, delta T, times our length of 525 millimeters. Line 1. Then we're going to add, so all of that plus, again, now we're doing delta 2 here. So we'll plug in these terms. So delta 2 is 6,000 newtons times 675 millimeters all over 78.54 millimeters squared times 115,000 newtons per millimeter squared, plus the thermal expansion, or in this case it's going to be contraction, but we're going to keep it positive here, plus 18.7, a coefficient of thermal expansion, times 10 to the negative 6th per degree Celsius, times our one unknown, delta T, times the length of bar 2, 675 millimeters. All of that added together equals 0. So now, if I were you, I would add this term and this term, bring it to the other side, then add the coefficients, so multiply these terms out, and then factor out a delta T. So I'm not going to do all the algebra. So solving for your only unknown, for delta T, they have to change by the same temperature. We get that the change in temperature equals negative 41.2 degrees Celsius.